Our lives are ruled by measurements. If you don't think so, try to get through your day without looking at a clock. We measure time as if our lives depend on it. And they do. Leave it to NIST to build the world's most accurate timekeeping instrument, the NIST F1 atomic clock. So how accurate is the most accurate clock on Earth?
We originally said, well, we want to get an accuracy of about 10 to the minus 15 out of this clock, and it's now at 3 times 10 to the minus 16. And that means that's the equivalent of the clock losing or gaining 1 second in about 100 million years.
Stephen Jeffords, with NIST's Time and Frequency Division, has led the F1 project from its inception in 1996.
We call this an atomic clock, and it's really not a clock in the way that you tend to think of a clock. It doesn't have hands, and it doesn't tell time. All it does is tell me how long a second is. It doesn't put a label on the second to say that it's 5 o'clock in the afternoon. It will just tell me the difference between 5 o'clock and 5:0001.
The standard second, like the meter, is based on a natural phenomenon: the oscillation between the nucleus of a cesium-133 atom and its surrounding electrons. Before the first atomic clock, NIST based the second on astronomical observations, and it was recorded as 1/86,400th of a solar day. But by the early 1900s, researchers had already concluded that the measurement was problematic.
So it turns out that the rotation of the Earth on its axis is not a very good clock. The Earth wobbles, it doesn't rotate at the same speed all the time. Sometimes it slows down, sometimes it speeds up. And it turns out the rate between the atomic clocks and using the Earth as a clock has differed by about 30 seconds over this 40 years. And 30 seconds is not that big a deal, but if you let this continue indefinitely, you end up with sunrise being in the afternoon and things like that.
The solution came in the late 1940s, while Nobel Prize-winning physicist Norman Ramsey was studying the frequency oscillations of atoms.
And along the line, he said, hey, wait a minute, if I can measure these frequencies this accurately, I can turn this around and turn it into a clock. I must know how fast it's ticking, because the ticking rate is the frequency.
In 1967, the world agreed to a new standard, the atomic second. The atomic second equals 9,192,631,770 oscillations in a cesium-133 atom. But building a device to accurately measure those oscillations wasn't easy. The clock must be able to first select only cesium atoms in their lowest energy state, then excite them into a higher energy state.
The cesium starts inside here, gets shot through this tube inside the clock, at which point there's a vapor, a gas of cesium atoms in there.
6 lasers directed into the F1's main chamber control the movement of the cesium atoms during the experiment. The next chamber has a microwave field. It's here that the atoms move into their excited state.
The difference between those two states is given in terms of a frequency as 9,192,631,770 cycles per second, and this process is repeated 24 hours a day, 7 days a week for about a month.
The clock counts the cycles, or ticks. And every 9,192,631,770 ticks is a second. The whole world is now dependent on this time measurement.
You don't need time which is good to 1 second in 100 million years in your everyday life, except for systems that you tend not to know run on time. Things like the global positioning system is absolutely dependent on atomic clocks. High-speed data transfer over internet lines and things like that depend on really accurate frequency representations because we have to agree about what the frequency of the transfer is.